Alright, let's get into light-dependent reactions. So, photosystem 2 acts first. The photon-excited electrons, so those are just electrons that have been hit by the light of photons and they get into an excited state. The energy gets transferred to the cytochrome complex. This is like the chloroplast version of um, the electron transport chain, like the whatever's after the citric acid cycle. Um, or not citric acids. This is like the start of respiration, but with photosynthesis. So the cytochrome complex is first. That uses some of the energy to pump the protons into the thylakoid space. So it's got its own proton gradient. Um, and then the electrons that are lost from photosystem 2 are replaced by an electron released from splitting water. Uh, Photosystem 1, photons excite the electron. Then the excited electron is transferred to a membrane-bound electron carrier. Um, the electrons are used to reduce NADP plus to NADPH. And the electrons lost from photosystem 1 are replaced from the cytochrome complex. Slide 13 here is a very good diagram that you should draw out for how this process works, because just hearing words doesn't help. You gotta actually draw it out. Um, Slide 14, here's another diagram. Cyclic photophosphorylation may also occur in plants. It contributes to the proton gradient, which helps you get ATP. It does not, however, produce O2, and it does not transfer electrons to NADP plus, which would become NADPH. You're gonna have to be like drawing a lot of diagrams. Slide 15, this is the proton gradient pump diagram. You don't have to obviously draw like all the little shapes and whatever, just draw like the different substances that are coming in and out. Proton accumulation. So, during the electron transport, protons accumulate in the thylakoid lumen. That's like that thylakoid empty space, kind of. Protons flow back into the stroma through the ATP synthase, which drives the synthesis of ATP. Um, Rule of thumb here, anytime there's a diagram, I'd highly suggest you draw it, because that makes it easier to understand. Um, so, granums, you remember they're the stacks of thylakoids. Um, and so this little diagram just shows you what's in the thylakoid, the chloroplasts, the what because there's more cytochrome complexes and photosystem 2s. They're all going to be like in between the stacks of thylakoids, as you can see. They're most abundant in the thylakoid membranes of the granum. Um, and then photosystem 1 and ATP synthase more so will hang out in the stroma, um, kind of exterior, or in the thylakoid membrane exterior to the granum. All right. Light and photosynthesis. So, the scientist Engelmann, he put light through a prism to make a rainbow, just so he could view like all the different colors of light. Um, he lit up a bunch of algae, and then he saw where the aerobic bacteria moved to. So doing that, he could see like what wavelengths of light bacteria preferred, because those were the ones where they could best photosynthesize. And as you can see, they preferred the more extreme red and purple, or red and blue shades of light, rather than the medium green. And that's why so many photosynthetic organisms are green, because that's the one shade that they don't absorb. Slide 19, that looks like an empty graph to me. I'm sure Dr. Briggs had you draw something out in lecture. Photosynthetic challenges, too much light can cause damage. Uh, can cause the the system to run out of NADP plus, so that some electrons get passed to oxygen, which is bad, because then you don't get ATP. Because when not enough NADP plus is available, and 10I chlorophyll can transfer energy to O2, um, or electrons can be used to reduce O2. Alright, so xanthophyll pigments, they're another type of pigment in plants. Um, they slow the rate of electrons that are fed into the electron transport, so they regulate the assembly line, so to speak. And they release heat instead. Um, I am gonna cut this video on the light cycle, and I will get into the dark cycle in the next video.